I am Andre Lasta and I will be presenting about voltage controlled oscillators. So what is a voltage controlled oscillator? It is an oscillator that can control its frequency using an external voltage. This is called the control voltage. By adjusting the control voltage, it is possible to change the oscillating frequency. Conventional oscillators use variable resistors, capacitors, and inductors to get the job done. Now, to get the frequency of the oscillator, these components must be tuned. Compare it to a voltage-controlled oscillator. It is much more flexible, easy to tune, and set up. Now, here we have a simple block diagram of a voltage-controlled oscillator. So at the top, we have our supply voltage, VCC. On our left is the control voltage, and it should output a frequency. And it is also possible to adjust using a microcontroller like an Arduino. So instead of our control voltage here, we have a digital to analog converter, which is controlled by the Arduino. Now, the frequency range of a voltage controlled oscillator ranges from a few hertz to 100 gigahertz. So its applications include phase locked loops, modulation and demodulation circuits, frequency synthesizers, and function generators. So there are two types of voltage controlled oscillators, and these are the harmonic oscillator and the relaxation oscillator. For the harmonic oscillator, its uh, output is sinusoidal, while the relaxation oscillator usually has a square, sawtooth, and triangular output frequency. And under the harmonic oscillator included are RC, the LC, and the crystal oscillator. So for the harmonic voltage controlled oscillator, any of the three harmonic oscillators mentioned earlier can be converted to a voltage controlled oscillator. So instead of tuning the capacitor or the resistor manually, if they are replaced with a voltage controlled element, then it can be used like a voltage controlled oscillator. So here we have a part of a Colpitts oscillator, the tank circuit, I think. So we have two capacitors, C1 and C2, and these are changed to the varactor diode, D1 and D2, and the input control voltage. So for the RC and LC oscillator, its output frequency is inversely proportional to the square root of the RC and the LC. Now, looking at its characteristic curve, we have um, when the control voltage is increased, the output frequency should also increase. And when the control voltage is decreased, the output frequency should also decrease. And we can observe this in the formula. F of t is equal to f naught plus k times vc of t, where f naught is the nominal frequency of oscillation, which is specified in the spec sheet, and k here is the tuning gain and or tuning sensitivity, also specified in the spec sheet, and this is usually expressed in terms of hertz per volt. So this is just a factor that will tell how much the output frequency will change with respect to the control voltage, VC. So for the relaxation voltage controlled oscillator, so instead of using a current, you will use a control voltage to charge the capacitor and dictating your timing. So an example of this is the stable 555 timer. We look here at pin 5, the control pin. Usually this is directly grounded with a capacitor as shown here. So instead of directly grounding this, we can replace this with the control voltage, and this reference voltage here, two-thirds of whatever the supply voltage is, this can be overwritten with the control voltage. And there you have a relaxation voltage controlled oscillator. Now, some specifications that we would want to look at when choosing a voltage controlled oscillator are these. So first we have the tuning range. The tuning range is defined as the range at which the voltage controlled oscillator can be tuned for. So looking at a sample spec sheet, we have here VCO, the control voltage, and its minimum as is at zero point 0.5 volts and a maximum of whatever the supply is. Looking up here, the supply voltage, VDD, we have a minimum of 3.15 volts and a maximum of 3.45 volts. So the control voltage will be at a range of zero point 0.5 volts all the way to, let's use the maximum, 3.45 volts. Looking at the curve here, the graph here, we can see that the output frequency only starts at zero point 0.5 volts and increases as we increase the control voltage all the way to 3.45 volts. And we can see here that the uh, frequency range of the voltage controlled oscillator can range from a few hertz all the way up to a few hundred megahertz. So it has a very wide range and it is very flexible. So next we have the tuning gain or tuning sensitivity. Um, Manufacturers typically will not give you a single number for the tuning gain. Why is that? So look, here is the graph of the tuning sensitivity for a sample voltage controlled oscillator. We see here that at 2 volts, the tuning sensitivity is somewhere around 1.5 megahertz per volt. And when we increase the control voltage at to all the way to 20, we can see that the tuning gain, the tuning sensitivity is already somewhere around 3.5. So comparing that, start at 1.5 all the way to 3.5. So we can see that the tuning gain really does change with respect to the control voltage used. Next, we have the supply pushing and load pulling. Now, this is very important for high frequency VCOs. Now, supply pushing is defined as the change in the output frequency with the change in the supply voltage. Now, ideally, the output frequency should not change when the supply voltage is changed, but in practice, this is not the case. So we want to eliminate that. So this can be minimized by using regulated power supplies and oscillator circuits with a high Q factor. These are oscillators that can oscillate for many cycles before stopping. So it just means higher stability. Now for load pulling, sorry, this is defined as the change in the output frequency when there is a change in the load. And again, ideally, the output frequency should not change when the load is changed. But in practice, that is not the case. Lastly, we want to take note of the spectral purity of the voltage controlled oscillator. So this is a very important specification for the VCOs. Now, sometimes the amplitude and periodicity of the output frequency can change even if the control voltage stays constant. And when we look at this change in the amplitude and periodicity of the output frequency in the time domain, this is referred to as jitter. And when we look at this in the frequency domain, this is referred to as the phase noise. Now, this is especially important in modulation and demodulation circuits. Now, before I end this presentation, I have a small demo of a voltage controlled oscillator circuit working in action. So here we have our voltage controlled oscillator, a very simple circuit. So we have two op amps, a single MOSFET, a single capacitor, and a few resistors. So here we have our supply voltage, 5 volts, and here is our input voltage, and this is ranging from, I think, from 0 volts all the way to 5 volts as well. So we can see here that when the control voltage is changed, then the output frequency also changes. So when we increase this value, this control voltage, the frequency, the periodicity of this increases. When we decrease this, the output frequency also decreases. So that is all for my presentation. I hope you appreciated it, and goodbye. Thank you.